So the last sample problem in chapter 18 gets us to think with a little bit more of an expanded view of what acids and bases are. So this is just kind of a summary slide from lecture. And a lot of people think about the Arrhenius definition of acids and bases, which means that acids are species that increase the H plus concentration in solution or have H atoms to donate to solution or contribute an OH group to solution. And unfortunately, it's a very limited or narrow kind of view of acids and bases. It fits things like hydrochloric acid and sodium hydroxide, but it actually won't allow us to think about things like amines, which don't have an OH group, or as we've just learned about in some of our sample problems, highly charged metals. So a little bit more of an expanded approach is taken by Bronsted and Lowry, right? So it talks about acids having protons to donate, but bases don't necessarily have to have hydroxide. They just have to be able to be capable of accepting a proton from solution. And again, if they take that proton from water, they'll leave behind hydroxide. So they do contribute to hydroxide in solution, but maybe not from kind of giving it of themselves. So a little bit more of an expansive definition. But kind of the more all-inclusive definition is thinking about Lewis acids and bases. And so again, as our sets and subsets here will kind of like allow us to think about, pretty much any traditional acid or base can still be classified as a Lewis acid or base. And we can define Lewis acids and bases in the following way. Acids are molecules that can accept an electron pair, and bases are species capable of donating an electron pair. And funnily, what that really means, and if we kind of look at our summary sheet here, Lewis acids are going to be species that have vacant orbitals, being able to accept lone pairs of electrons. So maybe they're metals that are charged, or maybe they're just species that are capable of either expanding their octets or have incomplete octets, like we see, for example, with boron. Or a classic Lewis acid is just a proton, right, being H+. Things that are positively charged might have space where other electrons can come in and form a bond. Lewis bases, again, are going to have lone pairs of electrons that they can donate to making that bond. So we're going to be looking for heteroatoms like nitrogen or oxygen to be serving as Lewis bases. And so this last problem just is fairly simple, just kind of looking at a few molecules and asking who's the acid and who's the base. So again, if we look at this first problem that we have here, H plus OH minus, generating water, fairly straightforward chemistry that we've seen here, right? We've got H plus here. This is going to be our acid. This has a vacant orbital that it can accept a lone pair of electrons in making that bond, right? Making that bond to that water molecule. And then, just like we saw with other kinds of chemistry, you're never going to have two acids that react. So if this guy is acting as an acid, it should be logical to have this guy behave as a base. And again, heteroatoms such as oxygen and nitrogen are going to have those lone pairs of electrons that they can donate then to make a bond with a molecule acting as a Lewis acid. Second one here, we've got chloride ion. Again, a molecule having lone pairs of electrons that it can donate, reacting with, and if I draw out the Lewis structure for this guy, right, we can see that boron has an incomplete octet. Now, boron's happy having an incomplete octet. If we think about where boron is in the periodic table, it only has 3 valence electrons, so it's happy only having 3 bonds. But that vacant orbital allows us to do chemistry. We can have this guy come in and form a bond there. And again, I'm drawing some structures out here to help kind of explain what goes on here. Okay, we're going to have this adduct form, BCl4. And this minus charge, again, is going to come because we've got a formal charge of -1 on that boron that only wants 3 valence, 3 electrons around it just to itself, and it has 4. So in this case, we're going to have chloride acting as our Lewis base, and this BCl3 acting as our Lewis acid. Our last problem here, again, having K plus 6 waters. This is, again, how we're going to form what we call hexahydrates or hydrated metal ions. Okay, in this case, potassium is going to be acting as our acid. It has a vacant orbital that we can have interactions with the lone pairs of electrons on these oxygen atoms. So this guy is acting as our base. But one of the things that we'll notice here is this guy, just to kind of pull back and think about some other problems that we worked through. This problem is going to have no contribution to pH. Okay, this adduct, just because we see that, that's not something where these water molecules are going to lose their protons and contribute to the acidity of the solution. This is not a highly charged metal. But again, being able to identify Lewis acids and Lewis bases is going to become really helpful as you move on next year to organic chemistry.